Hello, warriors. This is Miss Lemons again, and I'm going to be going over the second example that's on the stoichiometry cheat sheet, the BCA Table Cheat Sheet. Now, it doesn't have all of this extra stuff underneath and around. This is actually from the first example, but I decided to keep it up here so that we could go back and look at it as a reference. So let's take a look at this. It says dicarbon octahydride combusts completely with excess oxygen to form carbon dioxide and water. Use the mole ratios to complete the BCA table if 3 moles of C2H8 undergo complete combustion. All right, so we actually have a lot of great information to start with before we even get into math. Remember, we're trying to avoid the math for as long as possible. So I'm going to go ahead and put my substances down into my BCA table. And I'm also going to include those coefficients because they, remember, are the mole ratio. So that the 1, the 4, the 2, and then this 4 as well. And then we are going to go ahead and start filling in as much of this without doing math. Now, one thing that we should always remember is that products will always start with 0 moles in the before row. So take a look at what we've got here. Our products are on the right-hand side of the arrow. So over here is where we find our products. And because we haven't done any sort of chemistry yet, we know that both of these products are going to result in 0 moles. Oops. We also have some information about oxygen. It says here that it reacts completely with excess oxygen. So we know that we're starting with an excess. And remember, excess means that we're going to begin the reaction with an infinite amount of gas, and we will also end the reaction with an infinite amount of gas. So we can go ahead and just type in the word excess for before, and we can type in the word excess for after, because if you have an infinite amount and you use a little bit, you're still going to have an infinite amount. All right, so now we're going to figure out this first one. It says here that it's going to combust completely. When we see this word completely, we can assume that we are going to be using all of that substance. Remember, reacts completely, that means we're using all of it. And how much are we starting with? We are starting with 3 moles. So I know that before the chemical reaction takes place, I'm going to be starting with 3 moles of dicarbon octahydride. And according to the word problem, I'm going to be using all 3 moles. Now remember, column or row A after is just mathematically combining rows B and C to get A. So we would take 3 moles minus 3 moles, and we're going to end up with 0 moles. Okay, so at this point, we now have to do some calculations. But even before I do that, we can see if there's any of these that also have a 1 in front as a coefficient, because we know that if they have the same coefficient, then they should have the same moles. Unfortunately, we don't have the same coefficient for any of these, so we do have to do a little bit of calculating. That's okay though. The cool thing about this too is that we are absolutely going to be able to calculate using pretty much the same setup for everyone. So that is 3 moles of C2H8, which also means that if we're starting with that we are also going to have that be our starting value over 1. This is the same exact setup that we are going to use for every single one of these 3 calculations, okay? So if we start with oxygen, our unknown is going to be the amount of O2. So go ahead and type that in. Unknown, number of moles of O2. So if we are trying to get from moles of C2H8 to moles of O2, That means we need to be looking at the mole ratio between those two substances. Remember, our mole ratio takes the number of moles of one substance compared to the number of moles of another substance in a balanced chemical equation. Those numbers are the coefficients from the chemical equation, which is why I like writing them down. So our first half is going to be 1 mole of C2H8 for 4 moles of O2. And again, I got these numbers from up here and just placed them in this mole ratio. Okay, so this is pretty much our setup. We're going to go ahead and start placing our conversion factor. So we've got 3 moles of C2H8 on top. What's on top must come down. We're going to be using the same units, but we're going to pull from our conversion factor. So we're going to put 1 mole of C2H8 on the bottom. If we use 1/2 of our conversion factor on the bottom, we have to use the other half on top. So that means we're going to put 4 moles of oxygen on top, multiply across the top and across the bottom, and then divide the top and bottom. This is nice and simple. So we end up with 7 over 1. 7 divided by 1 is obviously 7. So our final answer for this would then be 7 moles of O2. Now remember, because this is in the C row, we need to make sure that we have the correct symbol. A positive symbol means that we are creating products. A negative symbol means that we are actively using reactants. So because this is a reactant, we want to go ahead and put a negative symbol in front of it because we are using that. All right, we're going to do the same type of calculation now for these last 2 boxes. Thankfully, because we are starting with the same exact value, we're using the same one that we were given. We don't want to use the one that we calculated just in case it was wrong. Our setup is going to be pretty much the same. So I just deleted the key parts and then I'm just going to repeat what I did, but this time for CO2. So this time our unknown is going to be number of moles of CO2. And then of course our conversion factor is going to be that mole ratio that we're familiar with. So if we have for every 1 mole of C2H8, how many moles of CO2? That would be 2 moles of CO2. So we're going to go ahead and add that to our conversion factor here. All right, now we're in business. Okay, so now that I have my SU and C, I could go ahead and start filling in the blank. I'm starting with what I know, which is 3 moles of C2H8. I'm going to drop my unit, so what's on top must come down. And then we can, once we've used 1/2 of our conversion factor on one side, we have to use the other half on top. I can go ahead and multiply across the top and across the bottom, then divide the top and bottom to figure out my final answer. Thankfully, this would be 6 over 1. And so anything divided by itself, we know is going to be anything divided by 1 is going to be itself. So we already know that this is going to be 6 moles. We have to determine whether we are gaining or losing those moles. Remember, this is a product and products are always being created. So we're going to have to put a plus symbol in front of this. Remember, mathematically, we just combine rows B and C like it's an addition problem. So 0 plus 6 is 6 moles. And then finally, this last box here, we actually don't need to do any math at all. Why? Because I see a 1-to-1 ratio here. You see, for every 4 moles of oxygen, there will be 4 moles of water produced. If there are 8 moles of oxygen, that means there will be 8 moles of water produced. If there are 40 billion moles of oxygen, then there will be 40 billion moles of water produced. So it doesn't matter what the number is, it should be the same. It's a mole ratio here, and we're dealing with moles here. So it's a mole ratio here. So it carries down here too, which means no math for us. That means we are going to be absolutely using this mole ratio, not using any math. We're going to type this in, and because we are products, we are gaining. So it'll be plus, and we have 7 moles of carbon or of water. Is that? Whoop. All right, 7 moles of water. And then, of course, we want to make sure that we add B and C together to get our final fill in the blank, 7 moles And that's how you can pretty much do more than half of the BCA table without actually doing any math beyond addition and subtraction. So the only ones that we had to do math for were these two boxes. Everything else we kind of figured out by just knowing the mechanics of a BCA table and understanding mole ratios.